So jump into text-based question answering. So what is text-based QA? There's kind of two varieties of QA, and both of them are really, really important. In text-based QA specifically, we read a passage and try to answer questions about that passage. And this is also called machine reading. So I'll kind of be using these terms interchangeably here. This can contrast to knowledge-based QA, which I'm going to be talking about a few classes from now, as I just mentioned, where we, in text-based QA, we're matching against an unstructured data source, and knowledge-based QA, we're kind of looking up things in a structured data source. So to give an example, if we have a question, who was the oldest US president to take office? This is a very salient question because it was the current president. So Biden is the oldest elected president. You can get this information from a Wikipedia article that explicitly states this. You could also get this from kind of a structured knowledge base. So this is a structured table that nonetheless gives you the same answer by sorting this column from age at start of presidency. These both have strengths and weaknesses. The strength of text-based QA is not all information that we want to have is in structured tables. In fact, much information that we want to have is not in structured tables or knowledge bases. So it'd be nice if we could be able to access this without doing, without having to prepare these sources. However, knowledge-based QA also has its own advantages, which is, for example, if you asked who was the second oldest president, that might not be written anywhere in text, or if it is written in text, who knows? Maybe it was written before Biden became president, and so now that information is out of date and incorrect. So there's kind of a trade-off between these two sources, so it's worth knowing about both of them. Okay, and I'm going to go into a few QA tasks, or maybe more accurately, formats of QA tasks, because there's quite a few different ways you could be doing QA. So, for example, we could have multiple choice QA, span selection based QA, close or fill in the blank style QA. And not information extraction. We're going to talk about this later. There's also another thing that I'm going to talk about is generative QA, but I forgot to add this to the bullet points here. So multiple QA, multiple choice QA is basically where we're given multiple answers and we need to pick which one of them is correct. And just to give an example, we have MC test, 500 passages, 2,000 questions about simple stories that look like this. So we basically have James the turtle was always getting in trouble, da, 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 da. And then we have some questions meant to test comprehension. What is the name of the troublemaking turtle? What did James pull off the shelves? And for each of these, we have 4 choices. There's also another data set that was created here at CMU that was pretty popular called RACE. This is 28,000 passages, 100,000 questions from English comprehension tests. So can anyone think of a place where you'd want to solve multiple choice questions in the wild? Like, let's say you had them in actual application. Standardized tests? Yeah, that's true, but like it's not super clear what the utility of having a machine solve a standardized test is. Any other ideas? Yeah. If you go to Chipotle and you're trying to order and you want to look at the menu and decide which one is most to your liking, that's a very creative answer that I had not thought of before. Yes. Any other ideas? If you need to classify something like a business entity under a certain category or something like that. Yeah, that's actually a good example. I think the best example of something like this would be essentially text classification, but where your text categories are not kind of given beforehand, so you don't have like lots of training data or something like this. So up until very recently, I would have said there's not actually a lot of good examples of where to use this in the wild, but recently there have been kind of like prompting style things where you pose a question and then you give multiple answers to solve text classification tasks. Like, what topic does this passage belong to? And then you say sports, news, whatever else. So, but I think compared to the other examples that we have, this is maybe a little bit less practical and more suited for like probing or text classification methods. A second variety is span selection. This was popularized by Squad, where basically there's 500 passages, 100,000 questions based on Wikipedia text, and you have questions like what causes precipitation to fall, gravity, and gravity is guaranteed to be something in the passage here. There's also another example like Trivia QA, which has 95K questions, 650K evidence documents or distance supervision. So basically, the idea is you take in a passage and a question, and you need to select a span within the passage. So what about this? Where is this used in the wild? Any ideas? Search engines, yeah, so exactly. Like the example that I just gave, here, you find a passage and you select the span Biden, and you could say Biden. Maybe you'd want to say Joe Biden or something like that, which is kind of a different story, but this is in fact essentially what Google is doing when it tries to return results directly. Okay. Closed questions. So to give an example of this, we have a CNN Daily Mail data set, and what it looks like is we have an original article that says like the BBC producer allegedly struck by Jeremy Clarkson, da, 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 da. And then at some point you have Oisin Taimon. And then the query is producer X will not press charges against Jeremy Clarkson, his lawyer says. And so this X is basically fill in the blank, and you want to fill in the blank here. And so these are called closed questions, and the answer is the thing that would appropriately fill in the blank in the statement. In the CNN Daily Mail dataset, they also made a harder version of this where they basically anonymized it to try to remove the actual entity names. And the reason why is they wanted to focus on kind of whether the model is able to read and reason about the passage, as opposed to whether it's like able to serve as a language model and just fill in blanks based on the knowledge it has a priori. So that's the thing on the right. So any ideas about where this would be used in the wild in an actual application? Not really? Yeah. Mm-hmm. Mm-hmm. Yeah, I think that's definitely true. I think another thing is if you have something like a masked language model or something like this, and you want to try to answer a question with a language model, this is one way you can formulate a question in a way that's conducive to having something like BERT answer questions. So I'm going to talk about a model that does this and uses that as a way to answer questions in a similar way as this like span selection method as well. Cool. So the next one is generative QA. So you generate an output not constrained in any way. So it's not constrained to be entailed by the input. To give an example, a famous data set for this is narrative QA, which is basically like, the question is, how is Oscar related to Donna? The answer is her son. And then we have a story. And you can look through, and Donna, at some point, it says, like, that's a good looking kid you got there. And then you can see that she, who is Donna, is looking at Oscar. So you need to kind of reason over this narrative to be able to answer this question. But it's answered in a very succinct way that's not directly written in the text. So this is a kind of interesting data set as well. This also kind of has similarities to like summarization tasks, because you're trying to take the input and summarize it in a very concise output, but you also have a query related to this as well. So can anybody think of where something like this might be used? Could be a search engine, I guess, you know, similarly. Could be a dialogue system where you want to ask a dialogue system an answer to a question, and the dialogue system provides that answer. And you don't necessarily want it to have to be entailed by, you know, like exactly the things she said in the previous section. One problem with this compared to all of the other methods that I've talked about so far is it's really difficult to evaluate. You know, we've talked about how natural language generation evaluation for things like machine translation or summarization is very hard. It's even harder here because now you need to know whether the answer it gave was factually correct, despite the fact that you have no constraints on that being, you know, exactly the thing that was written in the passage. So that makes evaluating these kinds of things pretty tough. But anyway, that's a different story. Cool. Any questions so far? Pretty straightforward. Okay. So then another thing I'd like to talk about is what is necessary for solving these kinds of problems. And basically, if we think about it, in many cases, we need to take a large amount of information and extract only the salient parts. And when I say a large amount of information, this could be as much as a relevant passage from a Wikipedia article that's like 3 to 5 sentences long, or it could be all the way to all of the information on the web, like, you know, what Google is trying to do in their search engine, for example. So depending on the amount of relevant context that you are provided, you'll need to have different approaches. Like you could have effective attention style approaches that try to, you know, identify the information within a short passage, or you could have things like retrieval or search-based approaches to retrieve information from a much larger set of data. Another example of something that is very commonly necessary is some variety of multi-hop reasoning or multi-step reasoning. I've tried to turn it into multi-hop, but I realize so the standard terminology now has settled on multi-hop, but when I made my slides 2 years ago, it wasn't settled yet. So I forgot to change this particular slide, but I'll call it multi-hop. So like, as I showed here, you know, in order to solve this question, you need lots of kind of jumping around the passage, looking at different pieces of information and putting them together. Cool. So attention models for machine reading. So basically, these are the things that kind of identify the salient pieces of content within the passage. And what we would like to do is we would like to encode the document in the question and generate an answer, or including a sentence or a single word. And the way we do this is we have, you know, like a document, we have a question, we encode it in some way to get a vector to predict the answer. But the problem is encoding whole documents with high accuracy and coverage is hard. And it's particularly hard if we don't know the question in the first place. So one really important thing to know about these sort of machine reading QA style tasks, text-based QA style tasks, is it's very common to essentially encode the document and the question at the same time, as opposed to encoding the document and encoding the question, and then trying to do some sort of matching between them. Because if you try to encode the document to answer every single possible question, it's really hard to kind of guess in advance what sort of information you would be needing. So an important first thing to know is that like these kind of joint encoding models are really like the state of the art in any kind of QA style task. This is one popular attempt that was done in early models of question answering. So basically what it would do is it would calculate document to context and context to document attention. And both representations were concatenated to word representations themselves in the document. So you would basically calculate the attention between the question and the document. And then you would calculate the attention from, the question from the context to the query, and the attention from the query to the context, and then concatenate all the representations together to make a prediction, particularly in span-based QA. So you'd predict the start and the end. So this is kind of a clever way you could formulate things. But now kind of the standard is just to throw everything into BERT or some variety of BERT and basically predict the start and end spans here. And one nice thing about BERT is, you know, you're doing joint encoding of all of the things all at once. So if there are any important interactions that the model should be learning, you know, it has the capacity to learn these and use them to make the final decision. Oops. So, you know, a long time ago, like 2 years ago, before BERT kind of became the standard, I would be introducing a lot of models here. But in reality, this is the main model that people are using in most state-of-the-art systems. Just they might have better pre-trained representations in one system than they have in another. So one other thing to know about is word classification versus span classification. In span-based models, we need to choose a multi-word span. This contrasts to where you're like identifying a single word. So really, this isn't done very much anymore, but you could have a machine reading formulation where you only pick single word tokens. There's still a few holdouts, like there's a benchmark called BAMA that tries to predict particular entities and that uses single words. But in reality, most interesting questions that we would want to answer are multiple words. So you need to pick multiple words. Another contrast is to things like named entity recognition. And in named entity recognition, we want to identify multiple spans within a passage. So span classification tasks are ones where we're identifying only a single span that we should be paying attention to. So that's a contrast to some of the previous things we've done. Okay, so this is the things for kind of span classification models. There's also generative QA models, and generative QA models are models that allow you to generate any output in any form, basically. So you feed in the input passage in the question, and you use the decoder to output the answer. So there's a really interesting, so to give an example, this is one example of something that you can do with this. So you can take in kind of a story and try to output her son. This is kind of the extreme example of generative QA models. But interestingly, in this paper, Unified QA, they demonstrate that actually generative QA models can be used to answer many of the other types of questions that we would want to be answering as well. So here we have like the input passage, and we have the input passage here. This is the evidence passage about Nikola Tesla. And at the very beginning of the passage, we also append the question. And then we train a model based on this input and output to output the answer. So despite the fact that the model has no restriction to actually output a span that's included in the passage, if you train it on examples where every time it outputs a span, it will output a span in the passage. So this is extractive summarization. The AB here stands for abstractive. This is basically like generative, what I was calling generative question answering. So here what they do is they basically do exactly the same thing. They append the question to the very beginning, and then they have the evidence passage after that. And they have an output. Now the output is not necessarily like limited to being an extractive output. For multiple choice, you can do exactly the same thing, but what they do for the with respect to this is they actually give the model multiple choices, and after they've given the model multiple choices, they output the output here. And what you can actually do is you can calculate the probability of all of these multiple choices and just output the one that has the highest probability. So this is a way to use these models to do multiple choice tests. And these can be multiple choice tests based kind of like on with no passage whatsoever. So this is kind of like a common sense reasoning thing where you're given no evidence passage to reference. Or you could also add an evidence passage like this and try to output it. And then they also have Boolean questions, which are similar. You have a question, a passage, and the output is yes or no. And so what they do is they basically turned a whole bunch of QA data sets into this formulation and just trained the model on all of them. So it's a single model. It's a pre-trained encoder-decoder model, T5 in particular, which I've talked about earlier. And the nice thing is now you have a model that can solve any of these question types. You can indicate what question type it is by adding like a tag at the beginning or something like that. And it benefits by being trained on all of the tasks at the same time. So the low resource tasks also have some extra training data, multitask training data to reference. So we've used this a bit in my own work, and it's a kind of nice model that does much better than just a regular pre-trained model by scratch. Cool. Are there any questions about this or any of the other things we talked about? Yeah. Yeah, what happens if the context passage is too long? So it's a very good question. There are different ways to solve this. I actually don't remember the detail from the Unified QA paper, but you can do things like truncate, just truncate the passage to be shorter. You can also do things like try to a priori retrieve which parts of the context passage are better. We're going to be talking about retrieval models later, like how people do that within individual passages. But I don't actually remember what they did here. It might be the case that just all of the passages are short enough or something. But yeah, that's a good question. Another thing is we're near the end of the class, we're going to be talking about like long document transformer models or long document like neural encoding models, and you could use those as well, and those scale to very long passages. Yeah. Can it answer that it doesn't know whether the answer is correct or not? Yes. Interestingly, there's a couple ways to do this. So I'll try to give some references. So there's a paper here on unanswerable questions in Squad. So Squad 2.0 basically has questions in it that aren't entailed by the passage. And I think if I remember correctly, I think what they do in Unified QA, although I'm not completely sure about this, is they also have that as an option for the output. Another thing, another example is our paper. And here we discuss, we actually use the Unified QA model in this. And basically what we do is we try to, for multiple choice questions and extractive questions, we try to check the model calibration, which I believe I've talked about before, right? So it's basically how well the model probability estimates match with the actual likelihood of being correct. And we examine this and also examine ways to kind of like improve the calibration here. So I think, long story short, there's two methods. One method is trying to identify when a question is not answerable at all based on the question. And another way to do that is to try to identify when the model has low confidence and not output an answer, despite the fact that it might actually be answerable. So those are both options. Cool. Any other questions? These are good questions. Okay. Let's go ahead. Okay, so another big issue is multi-hop reasoning. And multi-hop reasoning, basically, after you've focused on a particular example, you might need to get more information. So if you have something like this, a question, where is the football? And you have something like John went to the hallway and John put down the football. If you want to figure out where the football is, first you look at the football, then you look at John, and then you see, like, in order to figure out where the football is, you need to know where John was at this point. And then you look where John is, and then you look at the hallway. So you basically need to jump around the passage to find pieces of information here. One interesting thing is that kind of even large transformer models or other things like this aren't like really good at solving these answers, these kind of multi-hop questions if you use them as is. So there's a lot of kind of multi-hop reasoning data sets that you can use to test these things. And they're, for example, often labeled with supporting facts. So the most famous one, also created here at CMU, is Hotpot Qa. And basically the way it works is we have one paragraph, and then we have another paragraph. And we have some supporting facts that are required to answer, like what was the former band of the member Mother Lovebone, who just died just before the release of Apple. And you have this malfunction answer here. So these data sets are nice because they kind of test the ability of models to synthesize information together and turn it into an answer over multiple facts. One issue with these data sets is there were a couple papers, like this paper by Chen and Durrett, that pointed out that actually for a lot of the answers here, you don't really need to be doing multi-hop reasoning, especially if you're given these passages, because you can kind of just identify like the first rock band in the passage, and then you're done. You just need to see former band and find the first band in the passage, and you get a good. Yeah. What was the former band of the member of Mother? Yeah, yeah. Even humans have trouble with multi-hop things, yeah. So yeah, basically, this is a good paper to reference regarding the kind of like bias in these data sets. But there's a number of methods for kind of like explicitly, either explicitly or implicitly doing multi-hop reasoning. And what I mean by explicitly is for many multi-hop questions where you need to kind of answer multiple subcomponents in order to get the answer to the question, you can split them into multiple questions. So for example, there's this data set called the drop data set, which does, they basically came up with a language that allows you to decompose more complex questions into simpler questions. So to take an example, from what yard line did Shane Graham kick 2 field goals? You start out with Shane Graham. Then you find the field goals of Shane Graham. You find the number of yards of the field goals of Shane Graham. Then you find the number of yards of field goals for each field goal of Shane Graham. And then you find the number of yards of field goals of Shane Graham for which the number of, so you can see it gets kind of complicated, but basically by decomposing the question in this way, you can answer the original question, which is like which yard line did Shane Graham kick 2 field goals? And there's other examples like this as well. And this can be used for questions over images or passages or databases, for example. A slightly more intuitive way of doing it is you might just split the questions into 2 textual questions. And this could be done, for example, by human annotator or even by rules, syntactic rules or something like this. And so then what you can do is you can run this by a textual question answering system and get the answer for the first question and then use that answer for the first question to kind of help answer the second question. Sorry, I realize now that I probably should have an example of what this looks like on the slide. I don't, but you can look at the paper if you're interested in taking a look. Any questions about this? Okay. So now we can think a little bit about more implicit ways of decomposing questions. The most implicit way of decomposing a multi-hop question would be just to say, well, a transformer model has multiple layers. Hopefully a transformer model with multiple layers, and the first couple layers can, attend to the right things, and then in the next couple layers, it can attend to the right things. And then eventually, by the time you get to the end of the transformer model, it will have the correct answer. And that's not necessarily a bad thing to assume. A transformer model can model any function over text that you would like, theoretically anyway. So, it is possible. But in practice, they are not they do not achieve optimal accuracy by doing this for many varieties of questions. So sometimes it's better to give them a little bit of a nudge in the correct direction. So a kind of other implicit way that you can model these things is basically by using something like a memory network. And a memory network is a general formulation of models that access an external memory through attention. And so, for example, in this particular paper, they do attention, get the argmax over the attention. So basically, they get the word or token that the model is attending to the most. And then they do another step of attention, essentially, that allows them to get a next value that they would use. And you can do this for an arbitrary number of times. So it's basically attend, get the result of attention, attend again, get the result of the attention, etc. And then you can use both to answer the question. And this was kind of softened into a more continuous space where now you have this big memory store here. And when you try to answer a question, you do attention over the memory store and get attention weights. You get the outputs, you combine them into an output, and you do it over and over and over again until you're happy with the output, allowing you to answer the question. So what this does is basically now you have this big memory bank here that you attend to answer, you attend to use to answer like particular facts or something like this. This is an interesting method because you could think of this memory, you could think of kind of, I guess, the like transformer model or whatever else as your short-term memory or your immediate reading of the sentence. And you could think of this larger memory store over here as essentially your long-term memory where you store facts and you're looking them up. You're using the fact that you looked up to then reason about what you should be thinking about next. So I like the formulation a lot, and it's been used in quite a few models for like multi-hop reasoning, et cetera. Are there any questions about this? Or? Okay. There's also methods that allow you to like write to the memory as well. So you could think of an agent that is continuously learning, continuously acting in an environment and updating its memory and other things like that too. So I think these are kind of interesting and interesting models. Okay, another question is when to stop reasoning. So I think the most common answer to this, whether you're doing explicit question decomposition or implicit kind of multiple steps of reasoning like you do in a memory network or even in a transformer model, is a fixed number of steps. So it's like we decompose a multi-hop question twice into 2 questions, or we do 2 steps over our memory network, or we have 16 layers in our transformer. So it's always the same amount of reasoning, basically. Another thing you can do is, these are basically the same, so I'll just talk about them at the same time. So it's like you have some sort of predictive model that tells you when you're done reasoning. So this exists in all of the things that I talked about before as well. So it could be like, you continue decomposing the question until your model tells you, okay, you don't need to decompose it anymore. You could also have a memory network where it stops re-accessing the memory when the predictor has sufficient confidence in the answer, or you have a classifier that tells you to stop. And there's also things like early exit transformer models, which only use the first couple layers of the transformer, and then they can stop for efficiency purposes, for example. So you have a big, really deep 24-layer transformer, but if after the first 3 layers you're happy with your representations, and you stop. So these are all things that have been proposed in the language. Okay. Any questions about this? Also. Okay. So next, I'm going to talk about retrieval-based QA models. These are a really, really popular topic nowadays, like in the past year or so, and one that I'm actually really excited about too. And the reason why I'm excited about them is because if you think about how humans answer questions, none of us answer all of the questions, or at least now, none of us answer all of the questions we're asked by just thinking in our heads, right? So our intelligence is a combination of our actual brain and reasoning ability, and also a search engine. So the reason, so retrieval-based QA models basically simulate this in that they have an underlying model, which we can call kind of our like language model or parametric model or our brain. And then we have a big external like data store of data that we can query into and use to like augment our language model. And so there's a number of different ways to do this. The first kind of place where this was proposed was in course-defined or retrieval-based QA models by Choi et al. In 2017. And this was used specifically for reasoning over like Wikipedia documents. So you have a whole Wikipedia document, which is relatively long. It's like starting to get long enough that you wouldn't be able to fit it in your big like T5 model and still have memory on your GPU. So basically what you do is you first decide which sentences to be covered, and you do sentence selection, and you create a document summary, and then over that summary, you do answer generation. It says RNN here, but you could use anything else. So this is the basic idea. In this particular work, they trained it using reinforcement learning. So you basically try to make a selection of a summary and see whether the model is able to generate the answer, and that would help train your sentence selection model. One thing is that this is also kind of a variety of multi-hop reasoning. In a way, you reason about which evidence would be useful, and then you kind of actually generate the answer based on that. So I think that connection is interesting as well. This can also be spun up to larger scales, so like retrieval over all of Wikipedia instead of just an additional Wikipedia document. And I guess the first paper to do that was probably Chen et al. 2017. One very popular model now is the retrieval augmented generation model. And to go a little bit into the details about how this model works, it basically has a query encoder where you encode the query that you are trying to look up. You then have a retrieval model. And the retrieval model, what it does is it takes a query, it then searches for the nearest document using minimum inner product search or maximum inner product search. So it's finding the document that is most similar to this query here. And so that gives you a whole bunch of documents. And then based on the documents, you make predictions over the output. And each of the documents has kind of a probability. And then you marginalize over the probabilities of the outputs given all of these documents to generate the final answer. And this can also be used for other things like fact verification, et cetera, et cetera. So the nice thing about this is this actually allows you to train both models kind of end to end. And the reason why is because if you retrieve multiple documents and one of the documents was like better than the other at helping predict the answer. So like if one of the documents was really useful, another document was not very useful, you can backprop to increase the probability of the document that proved useful and decrease the probability of the document that proved not to be useful, training the query encoder, for example. You could also train the document encoder, but if you train the document encoder, you need to recreate the document index for all of Wikipedia, which is very expensive. So you need to kind of do that sparingly, I guess. There's also methods that scale this to multiple hops. So basically you do one step of retrieval, and then you do a second step of retrieval based on encoding the query and the document you retrieved in the first step. So that's also a possibility. So this is a kind of, I don't know if it's exactly state of the art, but it's a near state of the art model that you can download and use if you're interested. Cool. Yeah. How is the document encoder trained? So the document encoder you can use an off-the-shelf thing where it can be trained similarly to backprop into the to increase the probability of the documents here. I actually don't remember exactly how they do it for RAG, but I do remember how they do it for Realm, so I can explain it here. Realm is the next one. So for the retrieval, so in addition, you can also do retrieval with masked language models. So this is for generative QA tasks. Realm is a very similar thing for closed-style QA tasks. But actually, sorry, before I talk about Realm, I'll talk about this paper first. So basically, a language model can be used to solve closed-style questions. And this is an example. Dante was born in mask. And if you mask out the input here, you can try to answer the question. It's actually kind of fun to do this with like the online BERT demos if you want, and see what questions BERT can answer and not answer. However, one problem is actually language models aren't super good at memorizing facts. They're like, in fact, quite bad at memorizing facts and would get the answer wrong a lot of the time. So what Realm does basically is it formulates these masked language modeling tasks as masked language modeling plus retrieval. So they have this neural knowledge retriever that retrieves a document, and then they have the query concatenated with the document and do masked language modeling over that to predict the final answer down here. So this allows you to much more accurately solve closed-style tasks. With respect to how the document encoder is trained for this, they actually have a training process based on, like what I talked about before, how much a particular retrieved document improves the likelihood of getting the correct answer. So if the retrieved document gives you a better likelihood, it will be upweighted. If the retrieved document doesn't improve the likelihood, it will be downweighted. But in this particular paper, they have a separate process that's going through and continually updating the data store to make the data store from the new document encoder constantly. So you have one process that's training this language model here, and then you have another process that's going in and continuously updating the data store. So if this sounds really annoying, I think it probably is. I personally, when I've been doing research on these QA models, we've been trying to avoid changing the data store very much. So another option that you could do is you could have just like a standard BERT model or whatever your best document encoding model is. Keep that fixed and only train the query encoder. I think that's a reasonable choice of things to do, and it might hurt your accuracy a bit, but it probably wouldn't be disastrous, I guess. So, those are some options that you could do in that case. Does that answer the question? Any other questions? Yeah. Yeah, good question. So whether the document helps the answer or not is it actually falls out directly from the marginal probability or from the expected probability. And basically what we have is we have the document retriever is predicting the document given the query. And then we have the probability of the answer Y given the original query in the document. So this is the probability of the output given the input. And then we would take the negative log probability and have this be our loss function. And this is affected both by the retriever probability and by the generator probability. And through the magic of backpropagation, if our loss function is dependent on both of these probabilities, we can backprop into both of them and appropriately find the parameters that will maximize this probability. And good question. Are there any others? Okay. Great. Another thing that I found is very interesting is question answering with context. So basically, this answers questions in a sequence, so context from the previous questions can be used in the next answer. I talked about this actually, I think, a few times ago as an example of a research paper that is solving a particular problem, but I'll talk about it again here. And basically, these are questions that appear in the context of a conversation. And I feel like this is actually really important if you want to use this in like a chatbot or something like this, because you don't want the person to be required to re-ask the entire question from the very beginning every time they interact with a virtual assistant. So basically what this does is this takes the whole conversation and tries to encode the previous utterances and things like this. So this is an interesting task. Okay. So I'd like to, I think, finish up. I think this is the last section, but I would like to finish with a caveat about data sets. And I specifically want to talk about it from the context of QA, because I feel like the QA data sets are often created in a way that requires you to be particularly careful about like using them, essentially. So all data sets in NLP or any other area have their biases. So for example, they might be biased to a particular domain. They might have simplifications from the core task that you want to answer. But for reading comprehension type things, it's actually pretty hard to come across real large-scale copyright-free data sets. So it might be the case that Apple has lots of questions that were asked to Siri, and they might even have some annotated answers, but they might not want to release them because it's really important data for their company. And if they gave it to everybody else, they'd lose an advantage or something like this. So where can you get these data sets in a natural way? So one example is like reading comprehension questions, I guess, like a reading comprehension data set. Even that, the copyright may belong to a place that does reading comprehension tests. So you need to be careful about that. Yeah, I'll skip the second part because I'll talk about that. So because of this, essentially, a lot of the data sets that are created for question answering are created in a way to test a specific hypothesis, but they're also created artificially with questions that were not asked by real users, but rather asked for the purpose of testing whether a system can do something or not. And this is a very famous old example, the baby data set. And it's particularly, fortunately, people don't work on this anymore, but people, when they were working on it, would make claims that this allowed you to answer particular types of questions. But in reality, the questions were automatically generated through synthetic text aimed at evaluating whether a model can learn a certain characteristic of language. So like, for example, a thing with a single supporting set, 2 supporting facts, 3 supporting facts, 2 argument relations, etc. But the problem was, papers evaluated only on this extremely simplified data set and then made claims about the ability to learn language in general. So as I said, like this is not very popular. This is not a very popular data set anymore. It's partly too easy. It's also like, I think a lot of people have recognized that it has problems in it. However, for a lot of the data sets that we do have, they're still created by an artificial process. It's just not as obviously artificial as we have now. So it's a good thing to keep in mind, especially if you want to use QA systems trained on the data sets in a real system, for example. Another example is the CNN Daily Mail data set that was very popular. So for example, the CNN Daily Mail data set revealed that very few sentences required multi-sentence reasoning, and many were too difficult because anonymization or pre-processing caused them to be wrong. So many, like over 25% of the questions were essentially unanswerable because the initial pre-processing was broken. So another thing to be aware of is that models tend to very carefully fit the data that they are given, and they might not necessarily generalize well into other data sets if we don't have a naturally created data set. So to give an example, there's this examination by John Lang where they added a sentence or a word string specifically designed to distract the model. And it dropped the accuracy of state-of-the-art models at that time from 81 to 46. So they basically took the question, they replaced the entities in the question, and created kind of a statement from this question and added it to the end of a squad passage. And the model basically picked the wrong entity in this individual sentence. I guess something like it'd be 35% of the time. And this just demonstrates that the models had a very strong bias towards looking up the entity type that they were looking for and in picking the last one that appeared in the passage or something without doing any of the others. So, so I think this demonstrates kind of that models can be fragile. It also demonstrates that data sets we need to be a bit careful of, especially if they were created programmatically or with some programmatic components. Another thing that people have been looking at recently is they want to test a particular phenomenon. Like they want to test whether a model is able to do multi-hop reasoning. And so they ask human annotators to create questions that should require multi-hop reasoning. And you start out with the assumption that you would like a data set that's hard enough such that current models are not able to easily answer the questions. So the idea is that if you create a data set where current models do poorly on it, but humans do well, then you can basically create harder challenge sets that are easy, that would be better for measuring progress. So the process is they basically generate potential answers to a question from a language model. And they find the answers from the language model that a QA model does poorly on, and have humans filter these questions for naturalness. And basically what this does is because you're finding potential answers that the QA model does poorly on, you could create a harder test set. And because you're having humans filter for naturalness, supposedly they're natural. However, when actually looking at adversarial data sets, the examples can be artificially hard or noisy. And more importantly, they're not representative of the things that people would actually create in the real world. So you're skewing the distribution from the things that you actually want to be working on, or want your model to be working on well. So my, I guess, suggestion or philosophy with creating data sets is, if at all possible, it is best to not create your inputs to your model. And when I say not create, I mean you don't like hire somebody and ask them to create the inputs to the model. Because in every task you're going to be answering, you have your input and your output. It's definitely okay to be creating your output because you might want to be identifying a specific phenomenon, or you might want to have an annotation standard or something like this. But if you can get natural inputs that were created by some process not that you were doing, then that has a much more high likelihood of not being biased. And a really good example of this is natural questions. This is a data set by Google, where basically they created questions naturally from search logs, or they got questions from search logs that were asked enough, and they released them. They used crowd workers to find corresponding evidence for these questions, and then they created the answers. So we have some examples like this. What color was John Wilkes Booth's hair? And then you have a Wikipedia page, you have a passage, and then the answer. You also have a Boolean question. Can you make and receive calls in airplane mode? The answer is no. And also, why does Queen Elizabeth sign her name Elizabeth R? And there's a passage here, but actually the answer is not like directly included in the passage. So the answer is no. And so this kind of embodies the idea of wanting to work with data sets where the input is natural, because here the input are Wikipedia passages, those are natural, and also queries that came from query logs. This is harder because, obviously finding the appropriate questions in the wild is not a trivial task. So it's not something that we need to do all the time, but it's something that we could strive for, I guess. Okay, any questions? Yeah. Exactly, yeah. If the questions are the input to your model. If the questions were the output for your model, like in a question generation task, then I think that would be perfectly fine. Yeah, cool. Any other, so I had one more section. I thought I was finishing too early. And so here's the final section. So I want to talk a little bit about symbolic reasoning in neural nets. And I think this is really interesting because there are some really impressive things that neural nets can do nowadays. They can, translate extremely well. In many, many cases, they can do dialogue and other things like this. But one thing they're notably not very good at is symbolic reasoning, and specifically mathematical reasoning. So this is actually from Bob's presentation last time, so I can kind of skip over it a little bit. But basically, in traditional semantics, we have things like symbolic reasoning, like the stuff that Bob talked about. I really like this reference, Representation and Inference for Natural Language. It's from 1999. Yeah. Yeah, it's from 1999, which is obviously a while ago, but there's still a lot of insightful things in here, which is like how you can reason over discourses, how you can you can talk about all things, existing things, combine pieces of evidence together to derive other conclusions and stuff like this. So I like this a lot, and most neural networks are very bad at doing this. Well, they would fail on many of the examples from this book. One of the big issues always is how to control the inference so that it's not doesn't make anything like computation, and also doesn't infer a bunch of stuff that yeah, and so one of the big there are lots of problems with these methods here. Like controlling the search space so that you're searching over things that are actually plausible instead of kind of extraneous things and other things like that. But I guess the thing that I wanted to point out is, there's a lot of things in here that neural networks could not do well. There's a lot of things that neural networks can do very well that symbolic reasoning could not do well. So that's the whole motivation, I guess, for combining the two methods together. here's another example, a numerical computation. So this is a figure from one of these two papers, I think maybe the Wallace paper, where basically what they did was they tried to train a regressor that would regress from various types of neural embeddings to numbers. And they trained it on the numbers between, I believe, 0 and 500, sorry, minus 500 and 500. And then they tried to extrapolate to other numbers that weren't included in this training data. And you can see basically its predictions of the values of the numbers that it is embedding are just horrible, right? Like the moment you try to get out of the training distribution, it's not able to predict the value of a number at all, which kind of indicates that numbers are not represented systematically. At least the numbers outside of like 0, 1, 2, 3, 4 are not represented systematically in neural networks at all. So you can guess that if you asked a number, if you asked a neural network, like how many, Bob had $10 and he gave Jim $2 and Jane $3, how many dollars does he have now? It'll probably say 2 or 3. So basically, this sort of reasoning does not come naturally to neural nets. So there's a number of ways that this can be fixed. There's a nice data set that tries to test these numerical reasoning capabilities called the DROP data set. And it contains a bunch of different tasks like subtraction tasks and comparison tasks and other things like that. This is a model that was implemented on top of this drop data set. And basically what it does is it has a whole bunch of neural modules that try to do things like identifying places in the text that it should be paying attention to, or doing numerical operations over those places in the text, et cetera, et cetera. So it's kind of a system that's both neural, but it's also symbolic in that it can do symbolic operations and use those to inform other neural components later. So this is a good reference if this kind of area sounds interesting to you. Yeah, so that's all I have for today. Are there any final follow-up questions that people would like to ask? Or... Yeah.
So one interesting thing about that dichotomy is that you can think of like neural nets as doing the fast automatic things that people do. That's a very clear map on what neural nets do. Whereas the symbolic stuff is slow and discrete and hard for people.
Right, exactly, yeah. So this is a really, really good comment, which is like, we can think of the neural nets as doing the things that are really fast and easy for humans to do. And the symbolic stuff is doing the things that are hard for humans to do or would require a lot of thinking or things like this. And there's two examples of this that I talked about here. One is math. Humans are not, like, there are some humans who are good at math or calculating in your head. I am not one of them. Everyone outside of this room is bad at math, and I'm bad at math, so at least one person in this room is not good at math. Another thing is remembering lots of information. So humans can remember a lot of information, but not anywhere near as much as Google, right? So my current philosophy in designing things, in a way, not entirely, but in a way, is if it's really easy for humans to do without any sort of assistance, then maybe a neural network is going to be able to do it reasonably well also. But if it's something that humans are not good without any assistance, then you know, maybe we should be having an external component. Another thing is if it takes a human a really long time to do it, even if they can do it, like thinking logically or things like that, then maybe just running it through a 16-layer transformer is not enough. And then you'll need to be having something like a memory network that listens over and over and over again. So I think these are kind of the interesting challenges that we need could be thinking about as research problems. So, yeah. So. How much progress have researchers made on open-ended question answering? I think a lot. It depends what you mean by open-ended, but if you're talking about like queries to Google or something like that, it's way better in the past 2 years than it was, way better now than it was in 2019. Oh, yeah, so I think a lot of those actually, so there's two questions here. One is, is it something frequent where you can find the answer online, or is it something infrequent where you cannot find, you cannot easily find the answer online? So like here, why, anyone have a good example? Why do,
Well, things that existed before 1990 are very hard to do, like what restaurant was on Fed Street in 1985? I don't know if that's just a...
Yeah, no, I think it's more like why or how or something like that. But like, how do I update Windows? So we have something like this here that gives you basically the answers. So if it's something that you can look up, that's easy. If it's something that you can't look up, I'm trying to think of like the nearest neighbor in like NLP land, but I don't know if there's actually, this is a long research topic. There have been people who've been doing this for a while, but I'm actually not exactly sure what the most recent version of this would be. So if you like have an answer to this, I'd actually be interested in knowing. I think one issue is that this is even harder to evaluate than anything we talked about here. So yeah, it's a good question. Anything else? Yeah. So how common is it to use few-shot approaches with a like GPT style or just a language model for question answering? I think it's like becoming super popular now. It's like the research topic of 2021 maybe. How well does that work versus a model that's been actually trained on lots of data? I think the answer is it still doesn't work as well. But the appeal of it is if you want to rapidly try to do something, you just need to come up with like a few prompts or something like that and test it out and see if it works. So I think, yeah, if you want to ship a system, you're going to be better off creating training data. But if you want to try something new, it's certainly a great way to do it. Yeah. Anything else? Okay, great. Thanks a lot.